Close your eyes and imagine floating high above the world, drifting peacefully through the darkness of space. Below you, turning slowly in the infinite night, is a sphere of swirling blues and whites and greens. This is home. This is Earth. Our planet formed approximately 4.5 billion years ago from a spinning disk of dust and gas surrounding our young sun. In those early days, Earth was nothing like the world you know today. It was a molten hellscape, a ball of liquid rock glowing red-hot in the cosmic darkness, bombarded constantly by asteroids and comets. But within that chaos, something extraordinary was beginning. As millions of years passed, the surface gradually cooled, and Earth's very first crust began to form, a thin, fragile skin over an ocean of magma. This original crust was likely made of dark, dense rock similar to what we now find at the bottom of our oceans. It was Earth's first solid ground, though no foot would walk upon it for billions of years to come. Beneath your feet right now, if you could journey to the very center of our planet, you would travel nearly 4,000 miles down through layers of rock and metal. At Earth's core lies a solid sphere of iron and nickel, nearly as hot as the surface of the sun, around 10,000 degrees Fahrenheit. This inner core is surrounded by an outer core of liquid metal, and it's the movement of this molten iron that creates something invisible yet essential, Earth's magnetic field. This magnetic field stretches far out into space, forming a protective shield called the magnetosphere. Like an invisible guardian, it deflects most of the dangerous solar wind, streams of charged particles constantly flowing from the sun. Without this shield, that radiation would have stripped away our atmosphere billions of years ago, leaving Earth as barren as Mars. In a very real way, the swirling metal at the planet's heart protects every breath you take. The atmosphere itself is a delicate envelope, surprisingly thin when you consider the size of our planet. If Earth were the size of an apple, our atmosphere would be no thicker than the apple's skin. Yet within this fragile layer exists everything that makes life possible, the air you're breathing right now, the clouds that bring rain, the winds that shape our weather. That atmosphere is composed of roughly 78% nitrogen and 21% oxygen, with the remaining 1% made up of argon, carbon dioxide, and trace gases. But it wasn't always this way. Earth's original atmosphere, billions of years ago, had almost no oxygen at all. It was only after tiny organisms called cyanobacteria began producing oxygen through photosynthesis, in an event called the Great Oxygenation Event about 2.4 billion years ago, that our air slowly transformed into something breathable. Now let your mind drift to the water that covers our world. Approximately 71% of Earth's surface is covered by oceans, rivers, and lakes. If you could gather all of Earth's water into a single sphere, it would measure only about 860 miles across, surprisingly small compared to the planet itself. Yet within those waters exists the vast majority of all living space on Earth. The oceans contain about 97% of all water on our planet, while only 3% is fresh water, and most of that is locked away in ice caps and glaciers. The Pacific Ocean alone is so vast that it covers more surface area than all of Earth's land combined. If you stood on the seafloor in the deepest part, a place called the Challenger Deep in the Mariana Trench, you would be nearly 7 miles below the surface, deeper below sea level than Mount Everest rises above it. The pressure there is more than 1,000 times what you feel right now, enough to crush almost anything, yet life still finds a way to survive in that cold, dark world. Speaking of Mount Everest, our planet's surface is a landscape of incredible extremes. Earth's tallest mountain rises 29,032 feet above sea level, but even more impressive is Mauna Kea in Hawaii. When measured from its base on the ocean floor to its summit, it stands over 33,000 feet tall, making it technically taller than Everest, though most of it is hidden beneath the waves. These mountains, these ocean trenches, these continents themselves are all constantly moving, though far too slowly for you to feel. Earth's outer shell is broken into massive pieces called tectonic plates, and these plates drift across the surface at about the same rate your fingernails grow, just a few centimeters per year. Over millions of years, this slow dance has built mountain ranges, open oceans, and periodically brought all the continents together into supercontinents before breaking them apart again. The last supercontinent, called Pangaea, existed about 300 million years ago, and the continents have been drifting to their current positions ever since. And as those continents drift, they carry with them the story of Earth's deep past, written in stone. If you've ever held a rock in your hand, you've touched something that might be older than entire civilizations, older than humanity itself. Some rocks on Earth's surface are more than 4 billion years old, nearly as ancient as the planet itself. These ancient stones, found in places like northern Canada and Western Australia, are windows into a world so different from ours that it would seem like another planet entirely. The ground beneath you is always moving in ways you cannot perceive. Earth spins on its axis at about 1,000 miles per hour at the equator, carrying you through space even as you rest peacefully in stillness. Yet you feel none of this motion, cradled as you are by gravity and atmosphere. At the same time, our entire planet orbits the Sun at an average speed of about 67,000 miles per hour, racing through the solar system on an elliptical path that takes exactly 1 year to complete. We are all cosmic travelers, though we journey in perfect comfort. This orbit is not a perfect circle, but rather an ellipse, which means Earth's distance from the Sun varies throughout the year. We're actually closest to the Sun in early January, about 91.4 million miles away, and farthest in early July, at about 94.5 million miles. This might seem counterintuitive if you live in the Northern Hemisphere, where January is winter and July is summer, but it's the tilt of Earth's axis, not our distance from the Sun, that creates the seasons you know. That tilt is approximately 23.5 degrees, and it's the reason why summer warmth gives way to autumn's chill, why winter's darkness yields to spring's light. As Earth orbits the Sun, this tilt means that for half the year, the Northern Hemisphere leans toward the Sun, bathing in longer days and more direct sunlight, while the Southern Hemisphere experiences winter. Then, as Earth continues its journey, the situation reverses. Without this tilt, there would be no seasons, every day would be essentially the same length year-round, and the same regions would always experience the same weather. But Earth's tilt does something else remarkable. It creates the phenomenon of the midnight sun in polar regions. During summer months near the poles, the sun never fully sets, circling the horizon for weeks or even months. In the depths of winter, the opposite occurs, the sun never rises, and darkness reigns for equally long periods. Imagine standing at the North Pole on the summer solstice, watching the sun trace a perfect circle above you for 24 hours, never dipping below the horizon. The dance between Earth and its moon adds another layer of rhythm to our world. Our moon, which formed about 4.5 billion years ago, likely from debris created when a Mars-sized object collided with the young Earth, is slowly drifting away from us at a rate of about 1.5 inches per year. This might not sound like much, but over hundreds of millions of years, it means the Moon was once much closer to Earth than it is today. When dinosaurs walked the Earth, they looked up at a moon that appeared larger in the sky, and their days were shorter, only about 23 hours long instead of our current 24. The moon's gravitational pull creates the tides that rise and fall along our coastlines twice each day. As the moon orbits Earth, its gravity pulls on the water in our oceans, creating a bulge on the side facing the moon, and another bulge on the opposite side. As Earth rotates through these bulges, we experience high tide, and when we're between them, low tide. In some places, like the Bay of Fundy in Canada, the difference between high and low tide can be more than 50 feet, enough to transform the landscape completely twice a day. This same gravitational interaction has gradually slowed Earth's rotation over billions of years. In Earth's early history, a day might have been only 6 hours long. The friction created by tides slowly transfers Earth's rotational energy to the Moon's orbit, causing our days to lengthen and the Moon to drift farther away. Though the change is imperceptibly slow in a human lifetime, over geological time it's profound. Eventually, billions of years from now, Earth's rotation will slow enough that one side will perpetually face the Moon, just as one side of the Moon now always faces Earth. The Moon also stabilizes Earth's axial tilt, preventing it from wobbling dramatically over time. Without our Moon, Earth's tilt could vary by tens of degrees over millions of years, creating wild climate swings that would make complex life far more difficult to sustain. Our Moon is unusually large compared to our planet, the fifth largest moon in the solar system, and by far the largest relative to its host planet. In a sense, we don't just have a moon, we're part of a double planet system. Looking down at Earth from space, one of the most striking features is the thin blue line of our atmosphere glowing at the horizon. But Earth isn't the only thing orbiting our planet. Since humanity launched the first artificial satellite, Sputnik, in 1957, we've surrounded our planet with thousands of satellites. Currently, there are more than 8,000 active satellites orbiting Earth, with thousands more pieces of space debris, defunct satellites, spent rocket stages, and fragments from collisions. These objects orbit at various altitudes, from just a few hundred miles up to more than 22,000 miles away, where communications satellites maintain a geostationary orbit, appearing to hover over a single point on Earth's surface as they match our planet's rotation. Beneath all this human activity, beneath the thin veil of atmosphere and the dance of satellites, Earth continues its ancient rhythms. The planet breathes and cycles longer than civilizations, its continents drifting like ships on a sea of molten rock, its magnetic poles wandering and occasionally flipping, its climate shifting between ice ages and warm periods over hundreds of thousands of years. We are passengers on a living world, floating through the cosmos. And as Earth drifts through space, it carries with it an extraordinary gift, the gift of life. Our planet is the only place in the entire known universe where we have confirmed that life exists. Every living thing you've ever seen, every person you've ever met, every tree, every bird, every microscopic bacterium, all share this one precious world as their home. In the vast emptiness of space, Earth is an oasis, a garden floating in the void. Life on Earth is astonishingly diverse. Scientists have identified and named approximately 1.5 million species so far, but estimates suggest there may be anywhere from 8 to 10 million species in total, perhaps even more. Most of these undiscovered species are likely insects, fungi, and microorganisms living in remote rainforests, deep ocean trenches, or hidden beneath the soil. Every year, researchers discover thousands of new species, reminding us how much of our own planet remains mysterious and unexplored. The oldest evidence of life on Earth dates back approximately 3.5 to 3.8 billion years, found in ancient rocks in Western Australia and Greenland. These early life forms were simple, single-celled organisms, nothing like the complex plants and animals we see today. For most of Earth's history, roughly 3 billion years, life existed only in these simple forms. Complex multicellular life, the kind you can see with your naked eye, has existed for only about 600 million years, a relatively recent development in Earth's long story. Life exists in the most unexpected places on our planet. Organisms called extremophiles thrive in conditions that would seem utterly hostile, in boiling hot springs where temperatures exceed 200 degrees Fahrenheit, in the acidic waters of volcanic vents, in the frozen soils of Antarctica where temperatures plunge to minus 130 degrees Fahrenheit, and even miles beneath the Earth's surface in solid rock, where some bacteria live without sunlight, oxygen, or any connection to the surface world. Life, it seems, is far more resilient and adaptable than we once imagined. The deepest parts of the ocean, those dark abysses where sunlight never reaches, are home to creatures that seem like they belong to another world. Bioluminescent fish that create their own light, giant squid with eyes the size of dinner plates, and strange, translucent creatures that drift through the darkness. Scientists estimate that we've explored less than 20% of the ocean floor, which means the vast majority of Earth's underwater landscapes remain unseen by human eyes. There are mountains and canyons beneath the waves we've never mapped, ecosystems we've never studied, creatures we've never named. Earth's forests, too, hold countless secrets. The Amazon rainforest alone produces about 20% of the world's oxygen and contains an estimated 390 billion individual trees representing about 16,000 different species. Walking through a rainforest, you're surrounded by one of the most complex ecosystems on Earth, where the canopy high above creates its own distinct environment, and the forest floor below teems with decomposers breaking down fallen leaves and returning nutrients to the soil. A single tree in the Amazon might be home to hundreds of species of insects, birds, mammals, and plants, an entire community existing in the branches of one organism. But forests and jungles aren't the only places where life flourishes. Earth's soil itself is alive with invisible multitudes. A single teaspoon of healthy soil contains more microorganisms than there are people on Earth, billions of bacteria, along with fungi, protozoa, and nematodes, all working together to break down organic matter, cycle nutrients, and support the plants growing above. This hidden world beneath your feet is one of the planet's most vital ecosystems, yet it's one we rarely think about as we walk across it. The biodiversity of life is matched by the diversity of Earth's landscapes. Our planet contains virtually every type of environment imaginable, from the driest desert, the Atacama in Chile, where some weather stations have never recorded a single drop of rain, to the wettest place on Earth, Mawsynram in India, which receives an average of 467 inches of rainfall each year. These extremes exist on the same planet, shaped by patterns of wind, ocean currents, and the position of mountains and valleys. Earth's deserts, despite appearing barren, cover about 1/3 of the planet's land surface and are home to specially adapted plants and animals that have evolved remarkable strategies for survival. The iconic saguaro cactus of the Sonoran Desert can live for over 200 years and store hundreds of gallons of water in its thick stem. Desert creatures like the kangaroo rat can survive their entire lives without ever drinking water, extracting all the moisture they need from the seeds they eat. Life finds a way even in the harshest conditions. And then there are Earth's polar ice caps, vast frozen realms that hold about 68% of all the fresh water on our planet. The Antarctic ice sheet alone contains roughly 26.5 million cubic kilometers of ice, enough that if it all melted, sea levels around the world would rise by about 200 feet, reshaping coastlines and submerging many of the world's major cities. Antarctica is not just a frozen wasteland, it's a massive reservoir of frozen water, a testament to how much of our planet's water cycles between liquid, solid, and gas over geological time. As you rest here, breathing softly, you're participating in one of Earth's most essential cycles, the exchange of gases that has continued for billions of years. The oxygen you inhale was likely produced by a plant somewhere on Earth, perhaps a tree in a distant forest, or phytoplankton drifting in the ocean. The carbon dioxide you exhale will be absorbed by another plant, used to build its leaves and stems through photosynthesis. You are connected, through every breath, to the living systems of the entire planet. The web of life extends far beyond what we can see. Even the air around you is full of life, bacteria, fungal spores, and pollen grains floating invisibly, carried by winds that might have begun thousands of miles away. Some bacteria have been found living in clouds, high in the atmosphere, possibly influencing weather patterns in ways we're only beginning to understand. Earth's biosphere extends from the deepest ocean trenches to high in the stratosphere, a living envelope surrounding our world. The air that surrounds you, invisible and taken for granted, is constantly in motion. Earth's atmosphere circulates in great patterns driven by the uneven heating of our planet's surface. Warm air rises near the equator, where the sun's rays strike most directly, and cooler air sinks near the poles. This creates vast circulation cells that drive the trade winds, the westerlies, and the polar easterlies, wind patterns that have guided sailors across oceans for centuries and continue to shape our weather every single day. These winds carry more than just air. They transport moisture from the oceans to the continents, seeds from one forest to another, and even dust from one continent across entire oceans. Every year, approximately 182 million tons of dust from the Sahara Desert is carried westward across the Atlantic Ocean, with about 27 million tons reaching the Amazon rainforest. This dust contains phosphorus and other nutrients that help fertilize the Amazon soil, creating an invisible connection between the world's largest hot desert and its largest rainforest, thousands of miles apart. Water itself moves through Earth in an endless cycle, evaporating from oceans, forming clouds, falling as rain or snow, flowing through rivers back to the sea, and beginning the journey again. This water cycle has been operating for billions of years, and remarkably, the water you drank today is the same water that has existed on Earth since shortly after the planet formed. The water molecules in your glass might once have been part of an ancient ocean, frozen in a glacier during an ice age, drunk by a dinosaur, or risen as mist from a tropical waterfall. Water is constantly recycled, never created or destroyed, just endlessly transformed and moved around our planet. Earth receives an enormous amount of energy from the sun, about 173,000 terawatts of solar energy strike our planet continuously. That's more than 10,000 times the world's total energy use. Most of this energy is reflected back into space or absorbed by the atmosphere and oceans, but the portion that reaches Earth's surface drives nearly all life processes. Plants capture this energy through photosynthesis, converting sunlight into chemical energy that flows through food chains, from plants to herbivores to predators, sustaining the intricate web of life. The energy from the sun also drives Earth's weather systems, creating the storms, hurricanes, and gentle breezes that shape our days. A single hurricane can release as much energy as 10,000 nuclear bombs over its lifetime, powered entirely by the warmth of tropical ocean waters. These massive storms help redistribute heat from the tropics toward the poles, acting as part of Earth's natural climate regulation system. Though they can be destructive, they're also a vital part of how our planet maintains its energy balance. Lightning, too, is part of Earth's atmospheric drama. At any given moment, there are approximately 2,000 thunderstorms occurring somewhere on Earth, producing about 100 lightning strikes every single second, roughly 8.6 million strikes per day. Each bolt of lightning is incredibly hot, reaching temperatures of about 30,000 Kelvin, which is roughly 5 times hotter than the surface of the sun. That intense heat causes the air around the lightning to expand explosively, creating the thunder that follows. Lightning also plays an important role in Earth's nitrogen cycle, converting nitrogen gas in the atmosphere into forms that plants can use, essentially fertilizing the soil from the sky. Beneath the atmosphere's drama, Earth's surface holds another kind of water in its frozen forms. Glaciers, those massive rivers of ice, cover about 10% of Earth's land area and contain approximately 75% of the world's fresh water. These slow-moving giants shape the landscape as they flow, carving valleys and fjords, grinding rock into fine sediment, and leaving behind distinctive geological features when they retreat. Some glaciers move only inches per year, while others can flow several feet per day, their motion driven by the weight of ice accumulating on their upper reaches. The largest glacier on Earth outside of the polar ice sheets is the Lambert Glacier in Antarctica, which is about 60 miles wide and over 250 miles long. But glaciers exist on every continent except Australia, from the tropical glaciers of Mount Kilimanjaro near the equator to the vast ice fields of Patagonia and the towering glaciers of the Himalayas. These frozen monuments are ancient. Some of the ice in Antarctic glaciers fell as snow hundreds of thousands of years ago, containing tiny bubbles of ancient atmosphere trapped inside, frozen time capsules that scientists can study to understand Earth's past climates. Mountains themselves tell stories of Earth's dynamic nature. The Himalayas, home to Mount Everest and the world's highest peaks, are still rising, growing about 5 millimeters per year as the Indian tectonic plate continues to collide with the Eurasian plate. This collision, which began about 50 million years ago, crumpled the Earth's crust upward, creating the highest mountain range on our planet. One day, millions of years from now, these mountains will erode away, their rocks worn down by wind and rain and ice, their sediments carried to the sea, and perhaps someday uplifted again in a different form. Mountains are not permanent, they are merely a stage in the endless recycling of Earth's crust. Volcanoes offer another window into Earth's restless interior. There are approximately 1,500 potentially active volcanoes on Earth's surface, not counting the thousands of underwater volcanoes that line the ocean floors along tectonic plate boundaries. When a volcano erupts, it brings material from deep within the Earth to the surface, molten rock, gases, and minerals that would otherwise remain hidden beneath the crust. Volcanic eruptions have shaped Earth's surface throughout history, building entire islands like Hawaii and Iceland, and occasionally altering global climate when massive eruptions inject enough ash and gas into the stratosphere to cool the planet for years. The ground beneath you, solid as it seems, is made of rock that was once molten, once buried deep, once perhaps at the bottom of an ancient sea. Sedimentary rocks form from countless tiny particles settling over millions of years, layer upon layer, compressed by time and weight into stone. Limestone cliffs were once coral reefs in tropical seas. Sandstone was once beaches or desert dunes. Even the marble of ancient sculptures was once limestone, transformed by heat and pressure deep underground into something new and beautiful. Everything on Earth is connected through vast cycles, the rock cycle, the water cycle, the carbon cycle, each one operating on its own timescale, some completing their circuits in days, others taking millions of years. As you breathe slowly, resting peacefully, these cycles continue their ancient dance. Continents drift, water flows, mountains rise and fall, all moving to rhythms far slower than a heartbeat, yet never truly still. In the darkness of night, as you close your eyes, Earth continues its journey through space, spinning and orbiting, its surface constantly changing, its life constantly adapting, its systems maintaining the delicate balance that makes this world livable. You are part of this living planet, made of the same elements as the rocks and water and air, following the same physical laws, participating in the same cycles that have sustained life for billions of years. As night falls across half the planet, Earth's rotation carries you into shadow, away from the sun's direct light. But even in darkness, our planet glows softly. If you could look down from space at night, you would see the twinkling lights of cities, like constellations scattered across the continents, but you would also see something else, a faint natural glow called airglow. This gentle luminescence occurs when atoms and molecules in the upper atmosphere, energized by sunlight during the day, slowly release that energy as light throughout the night. Earth's atmosphere literally glows, though the light is too faint for our eyes to notice from the ground. The night sky itself reveals Earth's place in a much larger cosmos. When you look up at the stars, you're seeing suns like our own, scattered across vast distances. Our sun is just one of an estimated 100 to 400 billion stars in the Milky Way galaxy, and our galaxy itself is just one of billions of galaxies in the observable universe. Yet from all those worlds and all those stars, Earth remains the only place we know with certainty harbors life. The famous astronomer Carl Sagan once described Earth as a pale blue dot, a single pixel of light in a cosmic ocean, and yet it contains everything we've ever known. Earth's position in the solar system is remarkably fortunate. We orbit in what scientists call the habitable zone or Goldilocks zone, not too close to the sun where water would boil away, and not too far where it would freeze permanently. Earth sits at just the right distance, approximately 93 million miles from the Sun, where water can exist in all three states: solid ice, liquid water, and vapor. This seemingly simple fact is the foundation of everything: the oceans, the rain, the snow, the rivers, the clouds, all made possible by our planet's perfect positioning. But distance alone isn't enough. Earth's atmosphere creates what's known as the greenhouse effect, where certain gases like carbon dioxide, water vapor, and methane trap some of the sun's heat, keeping our planet warm enough for life. Without this natural greenhouse effect, Earth's average temperature would be about 0 degrees Fahrenheit instead of the comfortable 59 degrees Fahrenheit we actually experience. The planet would be a frozen, lifeless ball of ice. It's a delicate balance: too little greenhouse effect and we freeze, too much and we overheat. Earth has maintained this balance for billions of years, though it has shifted between warmer and cooler periods throughout its history. These climate shifts are written in layers of ice, rock, and sediment. Earth has experienced at least 5 major ice ages throughout its history, periods when global temperatures dropped and massive ice sheets covered large portions of the continents. The most recent ice age, which peaked about 20,000 years ago, saw ice sheets up to 2 miles thick covering much of North America, Europe, and Asia. So much water was locked up in ice that sea levels were about 400 feet lower than today, exposing land bridges between continents. Early humans walked from Asia to North America across what is now the Bering Strait, following herds of animals across a frozen landscape that has since vanished beneath the waves. Between ice ages, Earth experiences warmer interglacial periods, like the one we're living in now. These cycles are driven by subtle changes in Earth's orbit and axial tilt, patterns called Milankovitch cycles that occur over tens of thousands of years. The shape of Earth's orbit slowly changes from more circular to more elliptical and back again over a cycle of about 100,000 years. The tilt of Earth's axis also varies between 22.1 and 24.5 degrees over a cycle of about 41,000 years. And Earth's axis slowly wobbles like a spinning top, completing one full wobble every 26,000 years. These 3 cycles combine to create subtle changes in how much sunlight different parts of Earth receive during different seasons, gradually pushing the planet into and out of ice ages. Deep beneath the ice sheets of Antarctica and Greenland, scientists have drilled ice cores that extend back hundreds of thousands of years, creating a timeline of Earth's climate history. These cylindrical samples of ice contain layers, like tree rings, with each layer representing a single year's snowfall. Trapped within the ice are tiny bubbles of ancient air, volcanic ash from long-ago eruptions, and dust from distant continents. By analyzing these cores, scientists can determine what Earth's temperature and atmospheric composition were like hundreds of thousands of years ago, reading Earth's climate history like a book written in frozen water. Earth's magnetic field, too, has left its mark in rocks throughout history. As molten rock cools and solidifies, magnetic minerals within it align with Earth's magnetic field, essentially freezing a record of the field's direction at that moment in time. By studying these magnetic signatures in rocks of different ages, scientists have discovered something remarkable. Earth's magnetic field has reversed many times throughout history, with the north and south magnetic poles swapping positions. These reversals happen irregularly, sometimes every few 100,000 years, sometimes not for millions of years. The last reversal occurred about 780,000 years ago, And we're overdue for another, though there's no way to predict when it might happen. These magnetic reversals are preserved in the rocks of the ocean floor in a distinctive pattern. As new oceanic crust forms at mid-ocean ridges, underwater mountain ranges where tectonic plates pull apart, molten rock rises from below, cools, and records the current magnetic field. As the plates continue to spread apart, this creates a striped pattern of magnetic orientations in the rock, alternating between normal and reversed, spreading symmetrically outward from the ridge. This pattern was one of the key pieces of evidence that confirmed the theory of plate tectonics in the 1960s, finally explaining how continents could drift across Earth's surface. All of this history, the ice ages and warm periods, the magnetic reversals, the rising and eroding mountains, the opening and closing of oceans, has occurred while life has persisted on Earth's surface. Life has witnessed it all, adapting to each change, surviving catastrophes, evolving new forms, spreading into every available niche. Through ice ages and hothouse climates, through asteroid impacts and volcanic winters, through the slow rearrangement of continents, life has endured. The story of Earth is one of constant change occurring within an overall stability. The planet is never truly the same from one millennium to the next, yet it remains recognizable, livable, a home for countless generations of living things. Mountains rise where there were once plains. Seas flood what was once dry land. Deserts bloom with life when the rains return after centuries of drought. Everything flows, everything transforms, yet Earth endures. As you rest here in this moment, you're part of that story. The atoms in your body were forged in stars that died billions of years ago, scattered through space, gathered into the cloud that formed our solar system, incorporated into Earth as it coalesced, cycled through rock and water and air and countless living things before becoming part of you. You are made of ancient stardust, arranged temporarily into the pattern of a human being, experiencing this brief moment of consciousness on a planet spinning through the cosmos. The elements that make up your body, carbon, hydrogen, oxygen, nitrogen, and all the others, have been part of Earth's story since the beginning. Carbon, the foundation of all life as we know it, cycles endlessly through the planet. The carbon in your cells might have once been part of a tree in an ancient forest, then released as carbon dioxide when that tree decomposed, absorbed by a blade of grass, eaten by an animal, returned to the soil, dissolved in the ocean, and eventually finding its way into you. Earth contains approximately 1.85 billion gigatons of carbon, distributed between the atmosphere, oceans, soil, rocks, and living things, all moving slowly through interconnected cycles that have operated for eons. The rocks beneath your feet contain the vast majority of Earth's carbon, locked away in limestone, marble, and other carbonate rocks. These rocks formed over millions of years as marine organisms extracted carbon dioxide from the water to build their shells and skeletons. When these creatures died, their remains settled on the ocean floor, layer upon layer, eventually becoming compressed into solid rock. In a very real sense, the white cliffs of Dover and the limestone buildings of ancient cities are made from the bodies of countless tiny sea creatures that lived and died millions of years ago, their calcium carbonate shells transformed into stone. Fossil fuels, coal, oil, and natural gas, represent another form of ancient stored carbon. These energy-rich materials formed from the remains of plants and marine organisms that lived hundreds of millions of years ago. When these organisms died, they were buried under layers of sediment before they could fully decompose. Over millions of years, heat and pressure transformed them into the coal, oil, and natural gas we extract from deep underground today. When we burn these fuels, we're releasing carbon that was removed from the atmosphere during the Carboniferous period, roughly 300 million years ago, when vast swamp forests covered much of the planet. Earth's oceans act as enormous carbon reservoirs, absorbing about 25% of the carbon dioxide released into the atmosphere each year. The ocean's ability to dissolve carbon dioxide makes it a crucial regulator of Earth's climate. Cold water can hold more dissolved gas than warm water, which is why the polar oceans are particularly important carbon sinks. As ocean water absorbs carbon dioxide, some of it reacts with the water to form carbonic acid, which then breaks down into other chemical compounds. This process has been absorbing carbon dioxide for as long as there have been oceans, helping to moderate Earth's climate over geological timescales. But the ocean's capacity to absorb carbon dioxide is not infinite. As the concentration of carbon dioxide in the atmosphere increases, the ocean becomes more acidic, a process called ocean acidification. This affects marine life, particularly organisms like corals, mollusks, and certain plankton that build shells or skeletons from calcium carbonate. As the ocean becomes more acidic, it becomes harder for these organisms to construct and maintain their protective structures. Coral reefs, often called the rainforests of the sea, are particularly vulnerable. These underwater ecosystems support about 25% of all marine species, despite covering less than 1% of the ocean floor. Coral reefs are among the most diverse ecosystems on Earth, home to thousands of species of fish, invertebrates, and other marine life. The Great Barrier Reef off the coast of Australia is the largest living structure on Earth, stretching over 1,400 miles invisible from space. It's not a single reef but a complex system of nearly 3,000 individual reefs and 900 islands. Yet for all its size and grandeur, a coral reef is built by tiny animals called coral polyps, each one no bigger than a fingernail, working together over thousands of years to create these massive structures. Each polyp secretes a calcium carbonate skeleton, and as generations of polyps live and die, their skeletons accumulate into the reef structure we see today. These polyps have a remarkable partnership with microscopic algae called zooxanthellae that live within their tissues. The algae perform photosynthesis, converting sunlight into energy and sharing some of that energy with their coral hosts. In return, the coral provides the algae with a protected environment and access to sunlight. This symbiotic relationship is so important that without their algae partners, most reef-building corals cannot survive. When corals experience stress from warming waters or other factors, they expel their algae in a process called coral bleaching, losing their color and their primary source of food. If conditions don't improve, the coral eventually dies. Earth's biodiversity extends far beyond coral reefs, of course. The total biomass of all life on Earth, the combined weight of every living thing, is estimated at about 550 gigatons of carbon. Surprisingly, plants make up about 80% of this total biomass, while animals account for only about 0.4%. Bacteria represent another 13%, and fungi about 2%. Despite all the animals you see around you, despite humanity's dominance of the planet, We and all other animals are a tiny fraction of Earth's living matter. There are approximately 7.8 billion humans on Earth, with a total biomass of about 0.06 gigatons of carbon. We're outnumbered and outweighed by the quiet, rooted life of plants. Even more humbling is the realization that humans and our livestock now account for about 96% of all mammal biomass on Earth. Wild mammals, all the elephants, whales, bears, wolves, deer, and every other wild mammalian species combined, make up only about 4% of mammalian biomass. Just 10,000 years ago, before the agricultural revolution, wild mammals comprised nearly all mammalian biomass. The rise of human civilization has fundamentally altered the composition of life on Earth, changing which species thrive and which struggle to survive. Yet even in a world dominated by human influence, nature persists in remarkable ways. Seeds can remain dormant in the soil for decades or even centuries, waiting for the right conditions to sprout. The oldest verified seed to germinate was a date palm seed found in an ancient fortress near the Dead Sea. The seed was approximately 2,000 years old, yet when planted and provided with water, it sprouted and grew into a healthy palm tree. Life is patient. It waits. It endures through long periods of hardship, ready to flourish again when conditions improve. In the soil beneath forests, trees communicate with each other through vast underground networks of fungal threads called mycorrhizae. These fungi connect the roots of different trees, allowing them to share water, nutrients, and even chemical signals. A large tree might support younger trees in shaded areas by sending them nutrients through this fungal network. When a tree is attacked by insects, it can send warning signals through the network, allowing neighboring trees to activate their chemical defenses before the insects reach them. The forest, which appears to be a collection of individuals, is actually a community, connected beneath the surface in ways we're only beginning to understand. Trees themselves are ancient witnesses to Earth's history. The oldest living trees on Earth are bristlecone pines in the mountains of California and Nevada, with some individuals over 5,000 years old. These trees were already ancient when the pyramids of Egypt were built. They have lived through the rise and fall of civilizations, through changes in climate, through centuries of drought and storms, growing slowly in harsh conditions, adding one ring per year to their trunks. Each ring records the conditions of that year, wide rings in good years with ample moisture, narrow rings in drought years, creating a timeline that extends back thousands of years. As you breathe slowly, deeply, imagine the patience of such a tree, growing imperceptibly day by day, year by year, century by century. There is no hurry in nature's rhythms. Everything unfolds in its own time. Mountains rise grain by grain. Canyons form drop by drop. Life spreads and adapts generation by generation. The planet operates on timescales that dwarf human experience, yet it created us, nurtured us, and continues to sustain us moment by moment. Time moves differently for different forms of life on Earth. While a bristlecone pine might live for 5 millennia, adding one thin ring each year, some organisms live their entire lives in mere hours or days. Mayflies, delicate insects that emerge from freshwater streams and rivers, live as adults for as little as a few hours to a single day. They don't even have functional mouths. Their only purpose in their brief adult form is to mate and lay eggs before they die. Yet their aquatic larvae might live in the stream for a year or more before emerging. Life operates at every conceivable timescale, from bacteria that divide every 20 minutes to trees that measure their lives in millennia. The diversity of life forms on Earth is matched by the diversity of ways organisms survive and reproduce. Some creatures, like the immoral jellyfish, Turritopsis dohrnii, can theoretically live forever. When faced with physical damage, starvation, or other threats, this small jellyfish can revert back to its juvenile polyp stage and begin its life cycle anew. It's the only known animal capable of this complete cellular regeneration, essentially achieving biological immortality. While individual immortal jellyfish can still die from predation or disease, they possess the remarkable ability to age in reverse, a trait that fascinates scientists studying aging and cellular regeneration. Earth's smallest organisms are often its most numerous and most important. Bacteria and archaea, single-celled microorganisms without a nucleus, are found in every environment on Earth, from boiling hot springs to frozen Antarctic ice, from the deepest ocean trenches to high in the atmosphere. The total number of bacteria on Earth is estimated at around 5 nonillion. That's a 5 followed by 30 zeros. To put this in perspective, there are more bacteria on Earth than there are stars in the observable universe. And most of these microorganisms remain unknown to science. We've likely identified less than 1% of all bacterial species. These microscopic organisms perform essential functions that make all other life possible. Bacteria in the soil break down dead organic matter, releasing nutrients that plants need to grow. Cyanobacteria in the ocean produce roughly half of all the oxygen in Earth's atmosphere through photosynthesis. Bacteria in the digestive systems of animals help break down food and synthesize vitamins. Without bacteria, the cycles of nitrogen, carbon, and other essential elements would cease to function, and complex life as we know it could not exist. We often think of bacteria as harmful germs, but the vast majority are either harmless or beneficial, quietly maintaining the systems that keep our planet alive. Deep in the ocean, far from sunlight, entire ecosystems thrive around hydrothermal vents, cracks in the seafloor where superheated water rich in minerals and chemicals pours out from beneath Earth's crust. The water emerging from these vents can reach temperatures exceeding 750 degrees Fahrenheit, hot enough to melt lead. Yet even in this extreme environment, life flourishes. Bacteria that feed on chemicals like hydrogen sulfide form the base of these ecosystems, providing energy for tube worms, clams, crabs, and fish that cluster around the vents. These are some of the only ecosystems on Earth that don't rely on sunlight as their ultimate energy source. They're powered entirely by Earth's internal heat and chemistry. The discovery of hydrothermal vent communities in 1977 revolutionized our understanding of where life can exist. If life could thrive in such extreme conditions on Earth, perhaps it could exist in similarly extreme environments elsewhere in the solar system, in the subsurface oceans of Jupiter's moon Europa, or in the methane lakes of Saturn's moon Titan. The existence of these vent communities expanded our conception of the possible habitats for life and gave new hope to the search for life beyond Earth. Earth's geological activity, the volcanism, earthquakes, and tectonic movements, isn't just destructive, it's essential for maintaining conditions suitable for life. Volcanic eruptions release gases from Earth's interior, including water vapor and carbon dioxide, replenishing the atmosphere and oceans over geological time. Without this outgassing, Earth's water and atmosphere would have been lost to space long ago. Subduction zones, where one tectonic plate slides beneath another, drag carbon-rich sediments down into the mantle, removing carbon dioxide from the surface. Later, volcanic activity releases some of this carbon back into the atmosphere. This geological carbon cycle operates over millions of years, helping to regulate Earth's climate over deep time. The movement of tectonic plates also creates new habitats and drives evolution. When continents split apart or collide, populations of organisms become separated or brought together, leading to new species evolving in isolation or competing in newly connected ecosystems. The formation of the Isthmus of Panama about 3 million years ago, connecting North and South America, allowed species from both continents to migrate and intermingle in an event called the Great American Interchange. Similarly, when India collided with Asia and created the Himalayas, it altered global climate patterns and ocean currents, indirectly affecting life across the entire planet. Earth's rotation creates another subtle but important effect, the Coriolis effect, which causes moving objects to curve to the right in the northern hemisphere and to the left in the southern hemisphere. This effect is responsible for the rotation of hurricanes and cyclones, counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. It also influences ocean currents and wind patterns, shaping the distribution of heat and moisture around the planet. Without Earth's rotation, our weather patterns would be completely different, with air simply flowing from the equator to the poles and back, rather than creating the complex systems of high and low pressure areas that produce our varied weather. Ocean currents themselves form a global conveyor belt that circulates water throughout all of Earth's oceans. Warm surface water flows from the tropics toward the poles, where it cools, becomes denser, and sinks into the deep ocean. This cold, dense water then flows along the ocean floor back toward the equator, eventually rising to the surface again to complete the cycle. This thermohaline circulation, driven by differences in temperature and salinity, takes about 1,000 years to complete one full circuit around the globe. It distributes heat, nutrients, and dissolved gases throughout the ocean, playing a crucial role in regulating Earth's climate and supporting marine life. The ocean's surface moves with the wind, creating waves that travel thousands of miles across open water. When these waves approach the shore, they slow down as they encounter the shallow seafloor, causing them to grow taller and eventually break on beaches in endless rhythm. The sound of waves, that eternal rushing and retreating, has been a constant presence on Earth for as long as there have been oceans and shores. It's a sound that predates humanity by billions of years, and it will continue long after we're gone, the breath of the planet, inhaling and exhaling against the land. Beaches themselves are temporary things, constantly reshaped by waves and currents. Sand moves along the coast, carried by longshore currents that flow parallel to the shoreline. A grain of sand might begin its journey in a mountain, broken free by weathering, carried by a river to the sea, deposited on a beach, moved along the coast by currents, washed out to sea during a storm, and eventually deposited on another beach miles away. That single grain might make this journey many times over thousands of years, constantly moving, never quite finding a permanent home. Everything on Earth is like that grain of sand, temporary in its current form, but part of something eternal. The water in your body will one day return to the ocean or the clouds. The carbon in your cells will eventually return to the soil or the air, to be taken up by new life. The energy that animates you came from the sun, captured by plants, passed through the food you ate, and will eventually radiate back into space as heat. Nothing is truly separate. Everything is borrowed for a brief time, then returned to the great cycles that have sustained this planet for billions of years. As you rest peacefully, you can almost feel those cycles moving through you, the oxygen flowing in and out of your lungs, the water moving through your cells, the energy slowly burning to keep you warm. You are a temporary pattern in the endless flow of matter and energy that is Earth. The atoms that make up your body have been part of countless other things before you and will be part of countless other things after you. You are ancient and new at the same time, a unique arrangement of very old pieces. The cycles that move through you are part of much larger patterns that encompass the entire planet. Consider the journey of a single water molecule. It might spend thousands of years frozen in a glacier, then melt and flow down a mountain stream, merge with a river, eventually reach the ocean where it remains for centuries, evaporate into the atmosphere, drift as vapor in a cloud for a few days, fall as rain onto a forest, be absorbed by the roots of a tree, travel up through the trunk to a leaf, be released back into the air through the leaf's pores, and begin the cycle again. The average water molecule spends about 3,200 years in the ocean, just 9 days in the atmosphere, and varying amounts of time moving through soil, rivers, lakes, and living things before returning to the sea. Earth's rivers are the arteries of the continents, carrying water, nutrients, and sediment from the highlands to the seas. The Amazon River, the largest river by volume, discharges approximately 209,000 cubic meters of water into the Atlantic Ocean every second, more than the next 7 largest rivers combined. This enormous flow of fresh water is so powerful that it pushes back the salt water of the ocean, creating a plume of fresh water that extends over 100 miles into the Atlantic. Sailors can dip their buckets into seemingly open ocean and draw up fresh, drinkable water, miles from the nearest shore. Rivers shape the landscape in ways both obvious and subtle. The Grand Canyon, one of Earth's most spectacular geological features, was carved by the Colorado River over approximately 5 to 6 million years. The river cut down through layer after layer of rock, exposing nearly 2 billion years of Earth's geological history in the canyon walls. The oldest rocks at the bottom of the canyon are among the most ancient on Earth's surface, formed when our planet was less than half its current age. Standing at the rim and looking down, you're seeing a cross-section through time itself, each colorful layer representing a different chapter in Earth's long story. Rivers also build as well as carve. As they flow toward the sea, they carry dissolved minerals and sediment eroded from the landscape. When a river reaches the relatively flat terrain near the coast, it slows down and deposits this sediment, building deltas, vast, flat expanses of fertile land that extend into the ocean. The Ganges-Brahmaputra Delta in Bangladesh and India is the largest river delta in the world, covering about 41,000 square miles. These deltas are some of the most densely populated regions on Earth, their rich soils replenished annually by river sediments, supporting agriculture that feeds hundreds of millions of people. The Mississippi River Delta provides another striking example of how rivers reshape coastlines. Over thousands of years, the Mississippi has switched its course multiple times, building its delta in different directions as sediment clogged old channels and forced the river to find new paths to the sea. From above, the abandoned channels of ancient river courses are still visible, tracing the delta's history across the landscape. Currently, the river deposits about 500 million tons of sediment into the Gulf of Mexico each year, though dams and flood control systems have reduced this flow from historical levels, causing parts of the delta to sink and erode rather than grow. Earth's landscapes are shaped not just by water, but by wind as well. In deserts, wind sculpts sand into dunes that can tower hundreds of feet high and stretch for miles. These dunes are constantly moving, grain by grain, as wind picks up sand from one side and deposits it on the other. Some dunes migrate across the desert at rates of up to 100 feet per year, slowly advancing like waves frozen in time. The shapes of dunes, crescent, linear, star-shaped, depend on wind patterns, sand supply, and the surrounding terrain, creating an ever-changing landscape that tells the story of the winds that shaped it. The largest sand dunes on Earth are found in the bedtime-style desert in China, where some dunes reach heights of over 1,600 feet, taller than most buildings, rising from the desert floor like golden mountains. Between these massive dunes lie more than 100 permanent lakes, a seemingly impossible feature in one of the driest places on Earth. The water comes from underground aquifers, seeping up through the sand to create these oases. The contrast is surreal, towering dunes of shifting sand surrounding pools of clear water, supporting small ecosystems of plants, fish, and birds in the midst of an arid wasteland. Deserts, despite their harsh conditions, are home to remarkable geological features beyond dunes. In many deserts, you'll find ventifacts, rocks sculpted by wind-blown sand into smooth, polished shapes with sharp edges and facets, like natural sculptures carved by invisible hands. Over thousands of years, sand grains carried by the wind act like sandpaper, slowly wearing away softer rock and leaving behind harder material, creating formations that seem almost deliberately shaped. These wind-carved rocks are found on every continent, even in Antarctica, testimony to the power of wind and time working together. The patterns of wind and weather on Earth follow seasonal cycles that have remained consistent for millennia. The monsoons that bring life-giving rain to South Asia each summer are driven by the differential heating of land and ocean. During summer, the land heats up faster than the ocean, creating a low-pressure area that draws in moist ocean air. This air rises over the heated land, cools, and releases its moisture as torrential rain. The Indian monsoon delivers about 80% of India's annual rainfall in just 4 months, flooding rivers, replenishing groundwater, and enabling agriculture that feeds over 1 billion people. When the monsoon is weak or late, drought threatens. When it's too strong, floods devastate. Life in these regions has always depended on the monsoon's rhythm. Similar patterns occur around the world. In West Africa, the seasonal migration of the Intertropical Convergence Zone, a belt of low pressure near the equator where trade winds meet, brings the wet season that supports agriculture in the Sahel, the transitional zone between the Sahara Desert and the savannas to the south. In Southeast Asia, monsoons alternate direction with the seasons, bringing wet conditions in summer and dry conditions in winter. These predictable seasonal patterns have shaped human civilization for thousands of years, determining when to plant and harvest, when to travel and when to shelter, organizing human life around Earth's atmospheric rhythms. the atmosphere above you extends far higher than you might imagine. While most of the air is concentrated in the lowest layer, the troposphere, where all weather occurs, the atmosphere continues upward through several distinct layers. The stratosphere, which begins about 7 miles up and extends to about 31 miles high, contains the ozone layer, a region where ozone molecules absorb most of the sun's ultraviolet radiation, protecting life below from its harmful effects. Without this invisible shield, UV radiation would make the surface nearly uninhabitable for most complex life. Above the stratosphere lies the mesosphere, where meteors burn up as they enter Earth's atmosphere, creating the shooting stars you sometimes see streaking across the night sky. Most meteors are no larger than a grain of sand, but their incredible speed, often over 40,000 miles per hour, causes them to compress the air in front of them so rapidly that both the air and the meteor heat to thousands of degrees, creating that bright flash of light. Every day, Earth's atmosphere is bombarded by about 100 tons of dust and sand-sized particles from space, most of which burn up harmlessly in the mesosphere, never reaching the ground. Even higher, in the thermosphere and exosphere, the atmosphere gradually fades into the vacuum of space. There's no clear boundary, just a gradual thinning until individual molecules of gas are so far apart that they rarely collide. This is where the International Space Station orbits, still technically within Earth's atmosphere but in such thin air that it experiences almost no drag. The astronauts aboard see Earth turning beneath them, completing an orbit every 90 minutes, watching 16 sunrises and sunsets every day. From their vantage point, Earth appears as it truly is, a sphere of life and color suspended in darkness, wrapped in the thinnest veil of atmosphere, alone in the vastness of space yet teeming with activity, both living and geological. Hurricanes spiral over oceans, volcanic plumes rise into the stratosphere, rivers snake across continents like veins, and at night, the lights of cities trace the patterns of human civilization across the dark landscape. It's a view that reveals both Earth's beauty and its fragility. But you don't need to travel to space to appreciate this planet's wonder. It's there in every breath you take, in the solid ground beneath you, in the water you drink, in the food that nourishes you. You are inseparable from Earth, made of its elements, sustained by its systems, part of its story. As you settle deeper into rest, you can trust that these ancient systems will continue their work, that the cycles that have sustained life for billions of years will continue through the night and into tomorrow. As Earth turns through the darkness, carrying you gently through space, the planet beneath you continues its endless transformation. Erosion never stops. Rain falls on mountains, seeping into tiny cracks in the rock. When that water freezes, it expands, widening the cracks imperceptibly. Over thousands of years, this freeze-thaw cycle can split massive boulders into fragments. It's estimated that erosion removes about 24 billion tons of soil and rock from the continents each year, carrying it grain by grain toward the sea. Mountains that seem eternal are actually slowly dissolving, returning to the ocean as sediment, to eventually be uplifted and formed into new mountains millions of years from now. The sediment carried to the ocean doesn't simply disappear. It accumulates on the seafloor, layer upon layer, gradually compressing under its own weight. Over millions of years, these sediments transform into sedimentary rock, sandstone, shale, limestone, each layer preserving a moment in Earth's history. The oldest sedimentary rocks on Earth are about 3.8 billion years old, And within their layers, scientists have found chemical signatures that suggest life already existed when they formed. Even in Earth's earliest days, life had somehow emerged and begun its long journey of evolution and diversification. Fossils preserved in these sedimentary layers tell the story of life's changing forms. The fossil record shows that life has existed on Earth for at least 3.5 billion years, but for most of that time, it consisted only of single-celled organisms. It wasn't until about 541 million years ago that complex, multicellular life suddenly diversified in an event called the Cambrian explosion. Within a relatively brief period, perhaps 20 to 25 million years, most of the major groups of animals appeared in the fossil record. Before this explosion of diversity, the oceans were dominated by simple, soft-bodied creatures. After it, the seas teemed with animals sporting shells, exoskeletons, eyes, and sophisticated body plans. What triggered this explosion remains one of the great mysteries of evolutionary biology. Some scientists believe it was related to rising oxygen levels in the atmosphere and oceans, finally reaching levels that could support the energy demands of larger, more complex animals. Others point to the evolution of predation. Once some animals began hunting and eating others, there was strong selective pressure to develop protective shells, better mobility, and more acute senses. Whatever the cause, the Cambrian explosion fundamentally changed Earth, transforming it from a planet of microscopic life into one where complex organisms could be seen with the naked eye. The history of life on Earth has been punctuated by mass extinctions, events where a significant percentage of all species died out in a relatively short period of geological time. There have been 5 major mass extinctions in Earth's history, the most severe being the Permian-Triassic extinction about 252 million years ago, which killed approximately 96% of all marine species and 70% of terrestrial vertebrate species. The cause of this great dying remains debated, but likely involved massive volcanic eruptions in what is now Siberia, which released enormous amounts of carbon dioxide and other gases, triggering rapid climate change and ocean acidification. The recovery took millions of years, but life eventually bounced back, evolving new forms to fill the empty ecological niches. The most famous mass extinction occurred 66 million years ago at the end of the Cretaceous period, when an asteroid approximately 6 miles wide struck Earth in what is now the Yucatan Peninsula of Mexico. The impact released energy equivalent to billions of nuclear bombs, creating a crater over 100 miles wide and sending massive amounts of debris into the atmosphere. The impact triggered earthquakes, volcanic eruptions, and tsunamis, but the most devastating effect was the dust and soot that darkened the skies, blocking sunlight for months or perhaps years. Without sunlight, photosynthesis ceased, temperatures plummeted, and food chains collapsed. About 75% of all species went extinct, including all non-avian dinosaurs. But extinction creates opportunity. The disappearance of the dinosaurs, which had dominated terrestrial ecosystems for over 160 million years, opened ecological niches that mammals quickly filled. Before the extinction, mammals were mostly small, nocturnal creatures, living in the shadows of the giant reptiles. After the extinction, mammals diversified rapidly, growing larger and adapting to countless different lifestyles. Within 10 million years, a blink of an eye in geological time, mammals had evolved into forms ranging from tiny shrews to creatures the size of bears, occupying ecological roles once held by dinosaurs. This pattern of extinction and diversification has repeated throughout Earth's history, driving evolution in new directions each time. After each mass extinction, the survivors inherit a transformed world, and natural selection favors different traits than before. It's a brutal process, but it's also the engine of evolutionary innovation. Many of the traits we take for granted in modern animals, flowers and plants, feathers and birds, complex eyes, live birth in mammals, evolved either in response to mass extinctions or during the recovery periods that followed, when competition was reduced and experimentation was rewarded. Not all evolutionary change happens through mass extinctions, of course. Most evolution occurs gradually, through the slow accumulation of small changes over many generations. Natural selection acts on random genetic mutations, preserving those that enhance survival and reproduction while eliminating those that don't. Over enough time, populations can change so much that they become distinct species, unable to interbreed with their ancestors. Earth's incredible biodiversity, millions of species adapted to countless different environments, is the result of this process operating continuously for billions of years. The pace of evolution varies tremendously. Some species, called living fossils, have remained essentially unchanged for hundreds of millions of years because they're so well adapted to stable environments. The coelacanth, a large fish once thought to have gone extinct with the dinosaurs, was discovered alive in 1938, virtually identical to fossils 400 million years old. Horseshoe crabs have remained largely unchanged for 450 million years, predating trees, flowers, and dinosaurs. In contrast, other species evolve rapidly in response to changing conditions. Some insects have evolved resistance to pesticides in just a few decades, and bacteria can evolve antibiotic resistance in years or even months when exposed to strong selective pressure. Evolution is still happening all around you, though you cannot see it. Every living thing is slightly different from its parents, carrying new combinations of genes and occasionally entirely new mutations. Most of these differences make no significant difference to survival, but some do, and those are the ones that natural selection acts upon. Over your lifetime, you won't see species transform, but the process is always working, generation by generation, invisibly shaping the future of life on Earth. The timescales of evolution can be difficult to grasp. A human lifetime feels long to us, but it's less than a heartbeat in evolutionary time. Species typically exist for 1 to 10 million years before going extinct or evolving into something else. The human species, Homo sapiens, has existed for only about 300,000 years. We're newcomers, barely arrived on a planet whose story extends back billions of years. All of recorded human history, every civilization, every empire, every innovation, spans only about 5,000 years, a mere 0.0001% of Earth's age. Yet in that brief time, humans have spread across every continent, reshaped landscapes, domesticated plants and animals, and developed technologies that have fundamentally altered our relationship with the planet. We've learned to extract metals from rocks, to harness energy from fossil fuels, to split atoms, to send signals across the world at the speed of light. We've looked outward to the stars and inward to the structure of atoms. We've mapped the human genome and decoded the mechanisms of heredity. In our short time on Earth, We've learned an extraordinary amount about the planet that created us. And yet, there's so much we still don't know. The deep ocean remains largely unexplored. We're still discovering new species every year. We don't fully understand how consciousness arises from the physical matter of our brains. We can't predict earthquakes or volcanic eruptions with any precision. We don't know how life began, or whether it exists anywhere else in the universe. For all our knowledge, Earth still holds countless mysteries, secrets hidden in the deep sea, in ancient rocks, in the complex interactions of ecosystems, in the subtle workings of the atmosphere. There is comfort in this. The world is not fully known, not completely mapped and catalogued. There are still discoveries to be made, questions to be answered, wonders to be found. Earth remains, even now, a place of mystery and surprise, a planet that can still astonish those who take the time to look closely, to ask questions, to explore with curiosity and wonder. As you rest here in the darkness, the planet continues its ancient dance, spinning through space, harboring countless secrets in its depths and heights, in its living creatures and its ancient rocks. As you drift deeper into rest, consider the air you're breathing. The oxygen that fills your lungs right now was produced by plants and photosynthetic bacteria, but not recently. The atmosphere is so vast that the oxygen you inhale might have been released by a tree decades ago, or by ocean phytoplankton last year, or by an ancient forest centuries past. The atmosphere mixes slowly, and molecules of oxygen can remain in the air for thousands of years before being consumed by respiration or chemical reactions. Every breath connects you to countless other living things across time and space, all sharing the same air, all participating in the same ancient exchange. Earth's atmosphere has an invisible boundary where it gradually fades into space, but there's a more meaningful boundary much closer to the surface. The tropopause, which marks the top of the troposphere where weather occurs, is only about 7 miles high at the poles and 12 miles high at the equator. If you could drive your car straight upward at highway speed, you'd reach the tropopause in less than 10 minutes. Above this boundary, the air is so thin and cold that it can barely be called atmosphere at all. Nearly all of Earth's weather, every cloud, every storm, every gentle breeze, all of it happens within this remarkably thin layer, like a film of moisture on the skin of an apple. The clouds that drift through this thin layer come in countless varieties, each with its own character and story. Clouds form when water vapor in the air condenses around tiny particles of dust, salt, or smoke, creating droplets so small that they float rather than fall. A typical cumulus cloud, one of those puffy, fair-weather clouds, weighs about 1.1 million pounds, roughly the weight of 100 elephants, yet it floats effortlessly because the tiny water droplets are dispersed through such a large volume of air. The cloud you see is mostly air with a mist of tiny droplets suspended within it, each droplet barely 1/100th of a millimeter across. The water cycle that creates clouds is solar-powered. Each day, the sun's energy evaporates about 1,170 cubic miles of water from Earth's oceans, lakes, and rivers. This water rises as invisible vapor, forms visible clouds, and eventually falls back to Earth as precipitation. On average, a water molecule spends about 9 days in the atmosphere before falling as rain or snow. Some of this precipitation falls back directly into the ocean, some soaks into the ground to replenish groundwater, some is absorbed by plant roots, and some flows across the land as streams and rivers, beginning its journey back to the sea. The cycle continues endlessly, powered by sunlight, driven by gravity, connecting sky and sea and land. Rain nourishes more than just plants and animals. It also plays a crucial role in weathering rock and regulating Earth's climate over geological time. When rainwater combines with carbon dioxide in the atmosphere, it forms a weak carbonic acid that slowly dissolves certain types of rock, particularly limestone. This process, operating over millions of years, removes carbon dioxide from the atmosphere and locks it away in rocks and ocean sediments. It's one of Earth's natural thermostats. If atmospheric carbon dioxide levels rise, the planet warms, which increases rainfall and speeds up this weathering process, gradually drawing carbon dioxide back down. If levels fall too low, the planet cools, reducing rainfall and slowing the removal of carbon dioxide, allowing it to accumulate again. This negative feedback loop has helped keep Earth's climate relatively stable for billions of years. But climate isn't perfectly stable, it fluctuates on many different timescales. Over the past 2.6 million years, Earth has cycled between glacial and interglacial periods roughly every 100,000 years, driven by those subtle changes in Earth's orbit and axial tilt we discussed earlier. During the last glacial maximum, about 20,000 years ago, ice sheets covered nearly 30% of Earth's land surface, compared to about 10% today. Sea level was 400 feet lower, and the global climate was dramatically different. Many species that thrived during that ice age, like woolly mammoths and saber-toothed cats, went extinct when the climate warmed and the ice retreated. Climate change, operating on geological timescales, has always been a driver of extinction and evolution. Human civilization developed during this current warm, stable interglacial period that began about 11,700 years ago. The development of agriculture, cities, writing, and all the complexity of modern society happened during a period of unusually stable climate by geological standards. The same temperature patterns, the same monsoon rhythms, the same seasonal cycles have persisted throughout recorded history, allowing humans to predict weather patterns, plan harvests, and build permanent settlements. We sometimes take this stability for granted, but it's a remarkable feature of the particular geological moment we happen to inhabit. Evidence of past climates is preserved in many forms across Earth's surface. Tree rings record wet and dry years going back thousands of years in some cases. Ice cores from Greenland and Antarctica contain bubbles of ancient air, allowing scientists to measure atmospheric composition going back 800,000 years. Coral skeletons grow in layers like tree rings, recording ocean temperatures and chemistry. Lake and ocean sediments preserve pollen grains, revealing which plants grew in the surrounding region when each layer was deposited. Stalagmites in caves grow slowly over millennia, their chemical composition recording changes in rainfall and temperature. Earth is full of natural archives, written in stone and ice and wood, waiting to be read by those who know how to interpret them. The history written in these archives reveals that Earth's climate has varied dramatically over geological time. During the Carboniferous period, about 300 million years ago, atmospheric oxygen levels reached 35%, compared to 21% today. This high oxygen content allowed insects to grow to enormous sizes, dragonflies with wingspans of over 2 feet, millipedes up to 6 feet long. The reason for these giant sizes was simple. Insects don't have lungs but instead absorb oxygen through small tubes in their bodies. With more oxygen in the air, these simple respiratory systems could support larger body sizes. When oxygen levels later declined, giant insects could no longer survive, and they gradually became extinct, replaced by the smaller insects we know today. Earth's climate has also experienced extreme warmth at various points in its history. During the Paleocene-Eocene thermal maximum, about 56 million years ago, global temperatures rose by 5 to 8 degrees Celsius over just a few thousand years, rapid by geological standards. This warming was likely triggered by a massive release of carbon into the atmosphere, possibly from volcanic activity or the release of frozen methane from the ocean floor. The warming caused widespread changes in ecosystems, with tropical plants and animals spreading into polar regions, and many deep-sea organisms going extinct as ocean temperatures rose and oxygen levels fell. Eventually, over hundreds of thousands of years, natural processes removed the excess carbon from the atmosphere, and temperatures returned to normal. Earth recovered, but it took a very long time. These stories from Earth's past remind us that our planet is resilient but not unchanging. Life persists, but species come and go. Climates shift, continents drift, oceans rise and fall. The Earth you know is just one frame in a very long film, one moment in a story that spans billions of years and will continue long after humans are gone. But in this moment, right now, you are here, conscious, aware, able to contemplate the planet that created you. You are lying on a planet that is 4.5 billion years old, composed of stardust from even more ancient stellar explosions. Beneath you, tectonic plates drift slowly across a mantle of flowing rock. Above you, the atmosphere shields you from the harshness of space while allowing just enough sunlight through to warm the surface and power the cycles of life. Around you, millions of species go about their lives, each one a unique solution to the challenge of survival, each one connected to all the others through webs of interaction so complex we may never fully understand them. The water in your cells has cycled through clouds and oceans, rivers and rain, through countless other organisms before becoming part of you. The carbon in your bones was once carbon dioxide in the atmosphere, captured by plants, passed through food chains, and now temporarily residing in your body. The calcium in your teeth might have once been part of an ancient seashell, compressed into limestone, uplifted in mountain building, dissolved by rain, and carried by rivers to the sea, where it was taken up by your food and incorporated into your growing bones. You are not separate from Earth, you are made of Earth, animated by its energy, participating in its cycles. When you walk across soil, you're walking on the remains of ancient life and weathered rock, billions of years of history compressed beneath your feet. When you drink water, you're tasting the same water that filled ancient seas, that fell as rain on dinosaurs, that flowed in rivers long before humans existed. When you breathe, you're exchanging gases with the whole living planet, taking in what plants release, releasing what plants need. As sleep draws closer, let yourself feel that connection. You are not alone on this planet. You share it with millions of other species, from the smallest bacteria to the largest whales, from ancient trees to newly hatched birds. You share it with all other humans, past and present, all of us brief visitors on a planet that was here long before us and will endure long after. Earth will continue spinning through space, orbiting the sun, cycling its water and air and rock. Mountains will rise and erode. Rivers will carve new canyons. Species will evolve and adapt. The planet will continue its ancient rhythms, indifferent to individual lives but sustaining life itself, generation after generation, millennium after millennium. And in this moment, on this night, on this small world floating in the vastness of space, you are here, safe, resting, part of something infinitely larger than yourself yet intimately connected to it. Your atoms are Earth's atoms. Your water is Earth's water. Your breath is Earth's atmosphere, flowing in and out, connecting you to everything that lives. Let that knowledge comfort you. Let it quiet your thoughts. You are home. You have always been home. This planet that made you holds you now, spinning gently through the darkness, carrying you through the night, as it has carried countless lives before you, as it will carry countless lives after. Rest now. Be still. The earth continues its journey, and you are safe upon it. The ancient cycles continue. The sun will rise again. For now, there is only this moment, this breath, this peaceful darkness.